Now, I'm just going to go over a quick lesson on acceleration. So, just remembering the difference between velocity and acceleration. Velocity is going to be our distance or change in distance over time. Acceleration, on the other hand, is going to be our change in velocity over time, right? And when I say change in velocity, we're either talking about a car or object is speeding up, or it's slowing down, or it's changing direction. Think about when you're in a car and any time that your body is moving, right? Either being forced forwards, forced backwards, or forced to the side. So you can see in a car, pretty much every, I don't know, every way you can change the car's motion is an accelerator. So one way we can talk about change in velocity is by showing a change in velocity on a velocity time graph. Right, we see that two different cars can reach the same velocity but in two different times. So what we're going to get here is we're going to get a change in velocity, which is going to be our slope, and that slope is going to be our acceleration. Now notice with the units, we know that our change in velocity is going to be a rise in meters over second, and our change in time is going to be our run, which is in seconds. So you get meters divided by seconds, and we can rewrite that as meters per second squared. Right, because every second we're changing the velocity. So as we talked about before, right? If you have a distance time graph or displacement time graph, the slope of that line is going to give us velocity. In a velocity time graph, the slope is going to give us acceleration, right? Because this is going to be the change in distance versus time, and this is going to be the change in velocity versus time. Thinking about a motion map, you can kind of see, remembering each dot kind of represents where the object is at each second. So this would be 0 seconds, 1 second, 2, 3, 4, 5 seconds. So kind of think about what is happening with the motion here. All right, we see that it's speeding up. You can try this on your own. You can pause. All right, but ultimately what we're going to see with a displacement time graph is that the first few seconds, the displacement's not changing very much. And then it's getting further and further and further each second. So you can see here, right, so we're starting with a velocity of 0, and that velocity is increasing over time. Conversely, what about if that velocity is slowing down, right? So you can see our distances are getting less and less and less. So what would this look like on the displacement time graph or velocity time graph? We notice that initially we are moving quite a large distance, and then that distance gets smaller in the next second and smaller in the next second. Right? So what would that look like? We know in terms of velocity, we're starting out pretty high, and then we can assume that we're going to end pretty low. So displacement, we're going to see something that looks a little bit like this. It's still moving the positive. It's increasing, slowing down, all the way until we get about a horizontal line. All right. So a couple things here. We're going to introduce a few different symbols for our different variables. So D is going to be our displacement symbol. Our initial velocity, how fast an object is going at the beginning of a situation. We're going to use the symbol V with the subscript O or 0, right? Because that's kind of our initial. Our final velocity is just V, acceleration is A, time is T. Now, try to use those symbols to rewrite this initial formula here, just using the symbols. can see it there. Again, unit for acceleration is going to be meters per second squared. You can kind of see how we're getting that when we look at our units put together. All right, so in this case, one thing you can do is use our formulas to try and solve for this one. So our first thing that's always going to be helpful is creating a little chart so we can identify what our variables are. So what we have here is we have two different velocities and a time. And we're trying to find what's the acceleration. So we don't know the acceleration. We do know the time. Now we just have to figure out the velocity. So it's accelerating from 15 meters per second. So that's where we're starting. And it increases to 35. Okay. So we know in this case, what's happening here is that it is speeding up. All right. So if we put this into our formula, it's A equals V minus VO divided by time. So we should get A equals 35 minus 15 divided by 10. And you'll notice right on the top, we have 35 minus 15. So we're going to get a positive number here. Now this is one that you can probably mental math out. Right? 35 minus 15 is going to give us 20. And then 20 divided by 10 is going to give us 2 meters per second squared. All right. Now here's another one. Here we have a train that's slowing down. Now keep in mind, a complete stop is also going to be a type of velocity. All right. Now, remember, in this case, our train is slowing down, so our final velocity is actually going to be less than our initial velocity. Right? So our train is initially going 12 meters per second, and then it comes to a stop. Right? So if it's going to a stop, that means its velocity is 0. Right? Try to find the acceleration. We don't know that. We do know the time, which is 8 seconds. So we're going to get a formula that looks a little bit like this, right? Our final velocity is 0 divided by 12. Get 8 over here. Now notice, because it's slowing down, we're actually accelerating in the negative direction, right? Opposite the direction that we're moving. So what we should get is we should get a negative number here. Calculate it out. We get your acceleration is going to be negative 1.5 meters per second square, because it's basically just negative 12 divided by 8. All right. Now, just to do a little bit of algebra, what we can do is we can rearrange our formula to create a new formula where we can solve for velocity or final velocity. So we rearrange this formula, right? We multiply both sides by t, and then add the initial velocity. We end up with final velocity equals the initial velocity plus acceleration times time. Now, if you look at this formula, you notice it actually looks pretty similar to one of our patterns. So think about what that might be. You notice that if we kind of rearrange it a little bit, it looks like this. Now, whether you have the velocity, the initial velocity in front or behind the acceleration times time, doesn't really matter. All right, we could rewrite that with it at the end. There's a reason why we put it at the beginning, but this is just your typical linear formula. Now, reading a velocity time graph, you'll notice that here, our velocity is constant, right? It's not changing. Our initial velocity is the same as our final velocity, right? One thing you can notice is what type of shape do we end up with here? Right? So one thing that we talked about is we talked about using the slope of a line to give us a new value. Another thing we can look at is what is the area under a graph? What does that tell us? All right. In this case, we get a rectangle. And if you remember, the formula for finding the area of a rectangle is simply your width times your height, or length times width, whichever you want to use. So here, all right, it's been moving 80 meters per second for 10 seconds. So we get 8 times 10 to find the area of the area under the curve. You know, it's because this object's moving with constant velocity, we could still use our constant velocity formula, which was just v equals distance over time, which if we're solving for distance was simply d equals v times t, which again, is the same as area equals length times height. So if we want to know how far an object went on a velocity time graph, the area under the curve actually tells us that. So now we have three things, right? Graphs tell us three different things here. The slope of a displacement time graph or distance time graph gives us velocity. The slope of a velocity time graph gives us acceleration. And the area under the curve of velocity time graph gives us the displacement. Or distance traveled. All right, so what about if we have a case like this? First off, we can see here, what type of shape do we have? Now, what we have here is we just have a triangle. If you remember the formula for area of a triangle, that's going to be 1/2 base times height. So we have a height of 100 and a run of 80. So multiply those together and 1/2. And we're going to get 400 meters. Now, what we created here is we also created a little bit of a new formula. First off, you notice that the velocity is changing, right? We started at 0 and then we reached 100. If you want to find the average velocity, right, kind of what was our average speed over the time because it's changing, we could use this formula where we simply add our initial and our final velocities and divide it by 2. So in this case, right, the final velocity is 100, the initial velocity is 0, right? So divide that by 2 is just going to give us 50. Now again, that's basically just taking two numbers and finding the average. That's just your regular, find the mean. But if we take that average velocity and we multiply it by the time, like how long it's been traveling for, that is going to give us our distance. Now again, what this is this is just, once again, our area of a triangle formula, right? Because what we're getting here is we're getting our base, which is time, our height, which is going to be our velocity, and then divide by 2, which is what you do with the triangle, because triangle is just half of a rectangle. So what we just derived there is we derived a new formula, right? Which is going to be displacement equals the final velocity plus the initial velocity, all times time divided by 2. So you can try out this formula to figure out what is the distance traveled. Now keep in mind, in this case, we don't have acceleration and we don't need to find acceleration. This is a useful formula when you don't have acceleration, you're not being asked to find acceleration. Right? So we can solve a couple of these in here. Don't know this. Right, so D is going to give us our final velocity, which is 30 plus 0, times our time, all divided by 2. And so we're going to get 150 divided by 2. E is going to be 75 meters. All right, we try deriving a new formula here. And really from here, you guys can take it on for yourselves. I'll have a couple links in the Canvas page so you guys can kind of simulate acceleration, so you can use that to kind of further your understanding. Again, take this time to go ahead and consolidate these notes. Again, I'll try to get it consolidated into about 1 to 2 pages. Yeah, really 2 pages if you're just adding in some of these example problems. But you guys are also going to get a worksheet today that will be part of your notes in your binder. So again, whatever notes that you put into your notebook is up to you. And then what we're going to do in one of our next classes when I'm there is we'll consolidate all these new equations that you're being introduced to, because these equations are going to really carry over through most of the rest of our year.